So section 4.4 is all about using coordinates. This is where we really start getting into vector spaces being a coordinate map away from Rn. And that's what we're looking at in problem 32. In problem 32, we've got a set of polynomials. So 32. We've got P1 of t is going to be 1 plus t squared. P2 of t is t minus 3t squared. And P3 of t is 1 plus t, 1 plus t minus 3t squared. All right. So what we want to do is look at the coordinates of each of these vectors relative to the standard basis for capital P2. So we want to write these as coordinate vectors relative to the standard basis. So we're going to start by writing P1, P2, and P3 as coordinates relative to the standard basis 1t and t squared. The standard basis for capital P2. So the coordinates of P1 relative to the standard basis will just be 1, 0, 1, because it's 1 of this vector, 0 of this vector, and 1 of that vector. So I'm going to write it this way. I'm going to say P1, instead of P1 of t, which means it's a polynomial, I'm going to say P1 is this vector. The coordinates of P1 relative to the standard basis are 1, 0, 1. The coordinates of P2 relative to the standard basis will be 0, 1, negative 3. And the coordinates of P3 relative to the standard basis are 1, 1, negative 3. So these are the basis vectors, the coordinates of the basis vectors relative to the standard basis. Or coordinates of the vectors P1 of t, P2 of t, and P3 of t, which are polynomials, relative to the standard basis for P2. And we want to show that these three vectors form a basis for R3, so that we can conclude that these three vectors, polynomials, form a basis for P2. All right. If I write the matrix made up of these vectors, P1, P2, P3, so 1, 0, 1, 0, 1, negative 3, and 1, 1, negative 3, and find the reduced echelon form on our calculating machine. So first, and I have to go by rows, 1, 0, 1, close the row, open the next row, 0, 1, 1, 1, close the row, open the next row, 1, negative 3, negative 3, close the row, close the matrix, close the command, and delete the rest of it. We do, in fact, get the identity matrix. So we have a linearly independent spanning set. Since the matrix P1, P2, P3 has a pivot in each column and a pivot in each row, these three vectors span R3. So that tells us that these three polynomials span P2. So let's write that down to make sure we get all the words in the right places. Since the matrix P1, P2, P3 has a pivot in each row and column, so we'll say is row equivalent to the identity matrix, this set of vectors, the columns of this matrix, they span R3. Therefore, the set of polynomials P1 of t, P2 of t, and P3 of t spans P2. We just take the polynomials, write them as vectors. Polynomials in P2, we write them as vectors in R3, and we use a matrix. If we want, since P1, P2, P3 is a basis for P2, we can find Q by multiplying by the change of coordinates matrix. So Q will be the change of coordinates matrix from B to the standard coordinates multiplied by the coordinates of Q relative to B. So the change of coordinates matrix is 1, 0, 1, and then 0, 1, negative 3, 1, 1, negative 3. And we're just going to multiply this by the coordinates of Q relative to B, which is negative 1, 1, 2. This will give us the standard coordinates of Q. So it'll be minus 1, 0, and 2. So that'll be 1. I'm doing arithmetic, so probably going to be wrong. 0, 1, and 2 is 3. Negative 1 minus 3 is minus 4. Minus 6 is minus 10. Those are the standard coordinates of Q. So here, just to be very clear, this is not what Q is equal to. These are the standard coordinates of Q. But now we can say that Q of t, the polynomial, is 1 plus 3t minus 10t squared. Negative 1, 1, 2 are the B coordinates of Q. Now, to connect these two things together, the B coordinates of Q are the combinations of the polynomials. So if I take negative 1 times the first, times P1 of t, plus 1 times P2 of t, plus 2 times P3 of t, that is negative 1 times this polynomial, 1 plus t squared, plus 1 times P2 of t, which is t minus 3t squared, plus 2 times P3 of t, which is 1 plus t minus 3t squared. We see get negative 1 times 1 plus 1 times 0 plus 2 times 1. We get 1. Then we get no t plus 1t plus 2t is plus 3t. Negative 1t squared minus 3t squared is minus 4t squared. Minus 6 more t squared is minus 10t squared. We're looking at the problem in polynomials and looking at the problem in coordinates in R3. Oops. This is thinking polynomials. This is thinking in coordinates. We multiply by this the PB matrix to turn B coordinates of Q into standard coordinates of Q. So here's what always shows up on a test, and then it shows up again on the final. I give you a basis, some weirdo basis for P2. I say here are the coordinates of some polynomial relative to the standard basis. Find me Q of t. The big mistake is to just stop here and give me the standard coordinates of Q and not tell me what the polynomial is. Now that I've said that, you're going to be like, oh, well, I'm not going to make that mistake. But I assure you, history indicates that 1/3 of you will make that exact mistake. Even though we're saying, hey, we're just going to take P2 and make it look like R3 with coordinates, If I ask for a polynomial, you need to tell me a polynomial, not a set of coordinates. How's everybody, okay? In problem 10, we want to find the change of coordinates matrix from B to the standard basis in Rn. So we're given some weirdo basis. Uh, 306, 2, 2, -4, 1, -2, 3. If we want the change of coordinates matrix from this basis to the standard basis, I just take the standard coordinates of these basis vectors. So P relative, PB will just be 306, 2, -4, 1, -2, 3. The change of coordinates matrix from B coordinates to standard coordinates are the standard coordinates of the B vectors. We should check that this is in fact a basis by seeing if it is an invertible matrix, by seeing if it is row equivalent to the identity matrix. 3, 2, 1, 0, 2, -2, 6, -4, 3. It is. We're just wanted to check to make sure that we didn't have some sneaky question where they don't actually give us a basis for R3. So we get this this weirdo basis for R3. To change these into standard basis coordinates, we just make the standard coordinates of the B vectors. The change of coordinates matrix from B coordinates to standard coordinates. Let's write these down. The columns of the change of coordinates matrix from B coordinates to standard coordinates are the standard coordinates of the B vectors. The columns of the change of coordinates matrix from B coordinates to standard coordinates are the standard coordinates of the B vectors. These are all standard coordinates of the B vectors. What we can do is what you can do to check to see if it works is write a linear combination of these vectors and multiply that by this matrix, and you'll get the standard coordinates. And then try to solve the equation that will give you the B coordinates of some standard coordinates, and you'll see that it goes back around in circles. So if I have standard coordinates, I take the change of coordinates matrix from B to standard coordinates and multiply by my B coordinates. So you can start off with some B coordinates, multiply by this matrix, and you'll get standard coordinates. If you want to find some B coordinates, you're going to have to solve an equation. Notice that if we have the X, then we're solving for the coordinates. Any questions? This, of course, makes a lot of sense if we think about matrix multiplication by making a linear combination of the columns of the matrix using the entries in the vector as weights. That is why I cared so much about thinking about matrix multiplication in that way. Make X as a linear combination of the columns of PB using the entries in X with respect to B, or relative to B, as weights. That's exactly what we're talking about. And that's much better than the dot product because it helps us, it solidifies, it reinforces the way that we're thinking about matrix multiplication. The reason that I wanted to write this sentence, the columns of the change of coordinates matrix from B coordinates to standard coordinates are the standard coordinates of the B vectors. Because you see that we have multiple bases for the same space. So if we have a set of B coordinates for a B basis, and let's say another basis of weirdo vectors, C coordinates, if we replace standard coordinates with C coordinates, then the sentence tells us how to go from B coordinates to C coordinates. So later on, in whatever section has change of coordinates, the columns of the change of coordinates matrix from B coordinates to C coordinates are the C coordinates of the B vectors. All just goes together, just adding more stuff onto stuff we already know. Any questions? How's everybody okay? It only seems like a lot to remember because it's a lot to remember. And I'm asking you to do all these problems. And they're including all this new stuff. But it's really just new versions of the same stuff. I don't know if there's an idea in storytelling that there are only 7 stories and everything's just a variation of one of those 7 stories. That's what math is actually like. It's just, we just pile on. We take the old stuff and we just pile on some new stuff. It's a variation on the same thing. It's like Pachelbel's canon. It's just the same thing. We just add more stuff on top of it. Meanwhile, sitting at the bottom are the cellists just playing the same sequence of notes. Any questions? Comments? Snide remarks? All right, let's pause the recording here and then talk about how we can cover homework questions on the remaining sections in this chapter.